Greetings and welcome to Mercenary Math. Today's topic is portfolio optimization. Suppose you have some spare cash that you have acquired and you've paid off your student debts. You don't have enough to invest into real estate or some other lucrative venture, but you have more than is necessary for savings. So you decide you're going to put it into stocks. So I'm going to assume you go through the whole process of studying your fundamental analysis and you've whittled down your choices to N many stocks, where N is something around 10 to 18 stocks. And you like these for fundamental reasons like agreeing with the company and looking at their balance sheets and agreeing. Now your question is, in what mixture should you buy these stocks? Because you've heard of something called diversification. But at the same time, you don't want to lose possible returns. Welcome to the topic of portfolio optimization. So first, we start with a history lesson. Back in the 1950s, a guy called Henry Markowitz, along with two other colleagues, developed an optimization model describing this system. It's simply put, you maximize this expression, lambda, brackets, WT times mu, where mu is the average returns, minus 1 minus lambda, so the rest, and a variance term, while your weights are non-negative and they sum to 1. So that's kind of a simplex constraint. Now this development netted Markowitz and his friends the Nobel Economics Prize in the 90s. So what does it actually mean? So your lambda is a value from 0 to 1. It's the investor's fixed choice. It's somehow a measure of your risk aversion versus how greedy you are. 0 means you're all in on the making money, so you choose your most lucrative stock, and 1 means you just want to minimize your variance in the stocks. Number 2, as mentioned before, the W's are the weights that you put on certain stocks. So it's the value of your WI is the value of your IF stock relative to the value of your total portfolio. And we're assuming here you don't have the ability to short, which is you can't have a negative amount of stocks. And obviously it has to sum up to the total value. You can't have, the sum has to be equal to the parts. Well, the sum of the parts have to be equal to the whole. Now, what was that mu I mentioned? It's the expected returns, which in layman's terms is simply the average for each one of your stocks, averaged over some time period. So you're going to have N stocks, and you're going to have data from time period 1 to time period M, which you've selected for whatever reason, and you simply sum and divide by the total, but by the number of data points. Your covariance matrix, for convention, we simply normalize by subtracting the mean, and we just plug and play into the usual formula. So there's some implicit assumptions in the Markowitz model, several actually, but I will only focus on 2 for the purpose of this video. The first is we're assuming that the returns are distributed in a Gaussian fashion. You can look up what a Gaussian curve is, or a Gaussian distribution. And second more, we assume that the variance somehow relates to the risk, which is in truth a very hard to define parameter actually. So what does this look like visually? So there's a Gaussian curve with the variant, standard deviation in the top right corner, and it's increasing. And as you can see, rare events on the sides become more and more likely, and the top becomes shorter and shorter. Now, both of these assumptions are patently wrong in reality, as we can observe in data. But what does this actually now mean if we're going to use this antiquated model which doesn't fit reality? So the big consequence to you financially would be that the model makes rare events seem less common than they actually are. As a result, you could have some really bad losing streaks which could financially wipe you out. So what does this actually mean distributionally? It means you have what is called fat tails. You have your extreme events are more likely on the positive or on the negative side than you expect. So what are tails? So here's a Gaussian distribution, crudely drawn, and here I am coloring in what are called the tails. Don't ask me why they're called the tails. This is simply a convention in the field. So given that the model discounts these rare events, how do we extend it so that it does take them into account? Well, we could do this by adding what is called higher order moments, or colloquially as fat tails, namely skewness and kurtosis. So first we begin by recalling the old model. We have maximizing the returns, minimizing the variance, but now maximizing the skewness, which is given by capital phi, and minimizing the kurtosis, which is capital psi. They're given in matrix forms, but they're tensors in truth. And we still have our simplex constraints. We still have no shorting, and it has to sum to the whole. So the skewness matrix is quite an obvious generalization of the covariance matrix. We use the tensor product notation to illustrate this. And similarly, the kurtosis. So the skewness we saw in the GIF of the previous segment, it shifts the distribution from left to right, and the kurtosis is a bit more subtle. It's more like the variance is skewed. So it also makes the tails fatter or thinner. So we prefer thinner tails, no surprises, and consistent results. Now this new model is now called the mean variance skewness kurtosis portfolio optimization model. Quite a mouthful. And this extends the Markowitz model, or the mean variance polynomial portfolio optimization model. If you enjoyed the video, please consider liking and subscribing and checking out my blog. Link is in the description.